In this video, you'll learn how I/O standards drive the assignment of internal signals to the external pins of the FPGA. When you assign a signal from your design to a particular pin on the device, this is known as pin assignment. I/O pin assignment is how you design interfaces with the outside world, so it's important to get it right. You will learn details of commonly used I/O standards in FPGAs and how they are important to overall performance and system requirements. How to determine the type of I/O that needs to be used for various applications, and the 5 methods for making pin assignments and tracking I/O attributes. We will start by reviewing I/O standards and structures, and will then discuss the 5 methods for I/O pin assignment and attribute control in FPGAs. I/O standards affect pin assignments. What do you suppose are the most common source of FPGA failures or delays? In my experience, it is first, timing closure, secondly, high-speed interfaces like PCIe and DDR3, and then third, pin assignments and I/O errors. This is a little surprising, given that pin assignments would seem to be a fairly easy task. And it is, but people sometimes don't pay attention to all the details, and then mistakes are made. I/O standards vary greatly, even within one FPGA. Although the wide variety of I/O capabilities and characteristics in FPGAs allows for great flexibility, it creates challenges in keeping track of all the I/O assignments. I/O is organized in banks with one voltage reference for each bank. Plus 3.3 volts, 2.5 volts, 1.8 volts are common. The next bank may be different from the adjacent bank. The single-ended I/O are LVTTL or LVCMOS, with many variations including HTL, SSTL, GTL, etc. There are also differential I/O standards, typically LVDS, but also LVPECL, CML, etc., that require 2 pins per signal. One of the most important things to remember is that global nets are usually assigned to specific pins that can also be I/O. Board layout must use these pins as clocks are reset if global nets are to be used. One of the most common mistakes I've seen as a consultant is the PCB connection of a clock signal to a pin that has no access to the global network in the FPGA. This can be easily avoided. Single-ended signals have different voltage swings, even at the same voltage, depending on whether they are TTL or CMOS, as shown in this table. Although V input high and V input low are the same, V output high and V output low are not. For example, V output high minus V output low is 2.0 volts for TTL, but at least 2.6 volts for LVCMOS. Some parts have PCI compliant I/O with a clamp diode. 3.3 volt PCI inputs can be 5 volt tolerant with an addition of a resistor in series. LVCMOS has extensions to lower voltages for less power consumption. At 1.5 volts, the swing is V output high minus V output low, which is equal to 1.025 volts minus 0.4 volts, or 0.625 volts. There are also single-ended reference logic families, including SSTL and HSTL. These are stub series terminated logic and high-speed transceiver logic, respectively. The I/O is referenced not to ground like TTL or LVTTL, but to a common reference voltage. This increases the speed of the logic, but reduces the noise margin. So can you get increased speed and better noise immunity at the same time? Yes, with differential logic standards like LVDS and LVPECL. However, this comes at the cost of needing 2 pins for each signal. Use of differential logic standards is a growing trend as the speed of interfaces continues to increase. Here is a simplified version of the circuitry at a typical FPGA I/O pin. When driven by the external source as an input, the signal propagates to the input register or can bypass it directly to the FPGA logic fabric. When configured as an output, the pin can be driven directly by a register, and the output can be enabled or disabled to create a tri-state bus output. Here's a more detailed look at the I/O pin circuitry for the MAX-10, including a number of added delays. The core of the circuit is still 3 registers and an output enable. The I/O has characteristics like slew rate and current strength control that can be programmed at a variety of values. Other I/O characteristics are also important and need to be assigned on a bank basis, as they can vary from bank to bank. Drive strength can vary from 2 to 24 milliamps or even more. Slew rates can be set fast or slow. Some pins are hot swappable or input only or output only, while others are not. Some are DDR or PCI compatible, while most are not. Some are tri-statable, so they can be used to create external buses, others are not. How do we keep track of all of this? Like all good engineers would tend to do, we can use a spreadsheet. Quartus Prime comes with tracking tools that use a spreadsheet to make and document assignments. In Altera FPGAs, you can do pin assignment one of 5 ways. First, using Quartus GUI tools, either the pin planner or the assignment editor. Second, importing from an SDC file or an Excel spreadsheet file. Third, writing directives in an HDL, either Verilog or VHDL file. Fourth, automating by the use of a Tickle script. And lastly, importing from a PCB layout CAD tool. We will look at each of these in reverse order. Integrating the PCB layout CAD tool with the FPGA design flow can help reduce pin assignment errors, as design rule checks can help assure the circuit board and the FPGA assignments match. Many FPGA designers like to automate the pin assignment process with Tickle scripts as shown here. It is often helpful to include pin assignments in HDL code, as then the source file for the design and the pin assignments is together in one place. This can be done in both Verilog and VHDL as shown in these examples. Perhaps the most efficient way to make pin assignments is to make use of the FPGA vendor graphical tools. Here is a picture of the Altera pin planner. Summarizing what we've covered about FPGA I/O, FPGAs have extensive I/O capabilities, including many I/O standards and controllable circuit characteristics, but keeping track of the wealth of options leads to frequent errors. We can reduce I/O pin assignment errors by the use of methods that help document and track I/O usage. Differential logic standards like LVDS and LVPECL are increasingly popular in FPGAs, as they allow increased speed and better noise immunity at the same time. However, these standards require conductor pairs, further complicating the pin assignment process. In this video, we have learned details of commonly used I/O standards in FPGAs and how they are important to overall performance and system requirements, how to determine the type of I/O that needs to be used for various applications, and the 5 methods for making pin assignments and tracking I/O attributes.